We now enter the world of elementary number theory, which, as I mentioned earlier, is not a euphemism for easy number theory. Instead, it's an area of number theory that has its focus on fundamental questions about numbers, most of whose subtle answers do not involve advanced mathematical techniques. Here, with the notion fresh in our minds of an arithmetic progression, a list of numbers generated by successive addition, we open these lectures on elementary number theory by exploring the multiplicative cousin of arithmetic progressions. These are known as geometric progressions, number lists generated by successive multiplication. A simple example of a geometric progression arises by the mere act of doubling. 1, 2, 4, 8, 16, 32, and so forth is an example of a geometric progression. These numbers grow at a dramatically fast rate and possess enormous structure. We'll momentarily pause later in this lecture to consider how geometric progressions naturally appear in the world of music as a means of producing an even-tempered scale. This melodic excursion will involve notions that go back to the Pythagoreans and continue to confound piano tuners to this very day. Next, we'll turn to an extremely important and useful object in more advanced number theory, the sum of the terms of a geometric progression. Our exploration into these sums of numbers will include some amusing ancient stories that hold important mathematical morals. We'll then extend this addition of terms and consider the endless sum of all terms of certain geometric progressions and make such vexing ideas intuitive by visualizing such sums geometrically. The endless sum of a geometric progression is known as a geometric series. These series are fundamental in all branches of mathematics and science, especially, as we'll see in future lectures, in number theory itself. We'll then close this discussion with a whimsical illustration of the utility of infinite geometric series in the lives of lucky game show contestants, the happy fantasy of winning a large cash prize, and the unpleasant reality of paying taxes on that newfound bounty. Well, let's begin by recalling that an arithmetic progression is a list of numbers with the property that to get from any number to the next, we need only add a fixed value. As we'll discover as our course unfolds, these arithmetic progressions, while simple in structure, play an important role in our number theory story. Perhaps even more important, however, are the corresponding progressions in which the addition is replaced by multiplication. These progressions are called geometric progressions. To generate a geometric progression, we must be given the first number and then the constant multiple, which is known as the ratio, that generates the successive numbers on the list. For example, if we start with 1 and we're given a ratio of 2, then our geometric progression equals, well, we start with 1 and then we continually multiply our answer by 2 to get the next number. So 1, 2, multiply by 2 we get 4, multiply by 2 we get 8, multiply by 2 we get 16, 32, 64, and so forth. And it's easy to see that a general term in this geometric progression is given by 2 to the n power for some natural number n. The constant multiple, in the previous example it was 2, is called the ratio because the ratio of any two consecutive terms, the larger to the smaller, is always equal to that constant ratio. For example, notice that if we take a look at 32 and 16 that appear on our list and are adjacent, if I take 32 and divide it by 16, I get that constant ratio 2. Hence, that constant is called the ratio. In general, if we start with 1 and are given a ratio of, say, r, where r is just some number, then we could generate the geometric progression 1r, r squared, r cubed, r to the fourth, r to the fifth, and so on. We keep multiplying the previous answer by an extra factor of r. Well, these examples show us that a general term in a geometric progression that starts with 1 is of the form r to the n for some whole number n. Since the varying quantity is the exponent n, if r is a number bigger than 1, we say that r to the n grows exponentially. Very dramatic growth. And if r is a small number, bigger than 0 but smaller than 1, so r is between 0 and 1, we say that r to the n decays exponentially because it shrinks down faster and faster. For example, if we start with 1 and consider the ratio r equals a half, then we have a geometric progression that decays exponentially. We'd have 1, a half, a quarter, an eighth, a 16th, a 32nd, and so forth. Notice those terms are getting smaller and smaller and smaller. That would be exponential decay in this case. Well, let's take a moment to consider progressions in music and consider ratios of pitches. A musical interval is an octave if the two pitches have frequencies in a ratio of 2 to 1. An interval is a perfect fifth if the ratio of the two frequencies, the two pitches, is in a ratio of 3 to 2. So, for example, in modern Western music, the pitch A above middle C has a frequency of 440 hertz, which is usually said 440 hertz. Thus, the pitch A, one octave higher, has a frequency of 440 times 2, or 880 hertz. And the pitch E, 1/5 higher than A 440, has a frequency of 440 times 3/2, which equals 660 hertz. Well, in Western music, the chromatic scale begins at one pitch, say A, and progresses up in what are called half steps until it ends with the note that is one octave above the starting pitch. The pitches are derived from a progression of perfect fifths, starting with the first pitch. Well, a progression of perfect fifths is nothing more than a geometric progression with the ratio r equals 3/2. So if we start at A 440, we would have 440, and then 440 times 3/2, then 440 times 3/2 squared, then 440 times 3/2 cubed, then 440 times 3/2 to the fourth, and so on. And so, in fact, the numbers we'd get would be 440, 660, 990, 1,485, and so forth. Now, of course, these pitches are so high that only our pets would actually hear them, and so we really wouldn't be able to appreciate the music. So, in order to keep the notes within the 440, 880 hertz range, we divide the frequencies by 2 in order to lower the pitches so that they fall into the correct octave. Well, this process actually requires us to modify our attractive geometric progression, sadly, but happily we could then actually hear the pitches that are generated. So, why do we end up with a 12-note chromatic scale? Well, the answer to this question, which we'll discover for ourselves later in the course, involves irrational numbers. And we haven't even talked about those yet. And so we'll leave this as a musical and mathematical cliffhanger for now. But we will return to the question, why 12? Well, returning now to the geometric progressions that are the focus of this lecture, we note that it would be extremely useful to find the sum of the first few terms in a geometric progression, just as we did with arithmetic progressions. Now, if we consider the geometric progression 1, 3, 9, 27, 81, and so forth, here the the common ratio is 3. We multiply by 3 each time. Then the first 5 successive sums would be 1, 4, 13, 40, 121. And where do these numbers come from? Well, we just add up the terms in the geometric progression. So for example, 1 plus 3 gives us the 4, 1 plus 3 plus 9 gave us the 13, 1 plus 3 plus 9 plus 27 gives us the 40, and so forth. Now, a pattern is not immediately apparent, and you can see that we're moving into a more sophisticated world of number because now the pattern doesn't just pop out. This is going to now require some thinking. So to build some intuition, we'll explore a particular example with some great care. So let's actually consider the example we just looked at where we have a constant multiple of 3, a ratio of 3. And let's let S be the sum of the first 5 terms. So S will equal 1 plus 3 squared plus 3 cubed plus 3 to the 4th. So we have all those numbers, which, by the way, equals 121. Let's just keep that in the back of our heads. Well, here's the wonderful trick that's going to allow us to simplify this object. Let's now multiply both sides of this equation by 3. When I multiply the left-hand side by 3, I'm left with 3s. And when I multiply the right-hand side by 3, we see that every single term in that sum gets hit with another factor of 3. And if you notice what happens, the 1 when multiplied by a 3 equals 3. The 3 when multiplied by a 3 equals 3 squared. And it's kind of like those late night programs where as a new guest comes on, the old guests shift down. We just shift everyone down 1. So I see 3 plus 3 squared plus 3 cubed plus 3 to the 4th. And that last term, which originally was 3 to the 4th, when I multiply it by an extra factor of 3, becomes 3 to the 5th. Well, if we line these things up and now subtract the two equations, on the left-hand side, what do I have? I see 3 s's, and I'm subtracting 1s. So that's 3 minus 1 times s. On the right-hand side, notice that all the terms in the middle there, in the interior, align perfectly and actually add to give 0. 3 minus 3, 3 squared minus 3 squared, 3 cubed minus 3 cubed, 3 to the 4th minus 3 to the 4th. All we're left with is, on the very top, that 3 to the 5th, that dangling term way off to the right. And then, on the bottom, we're subtracting that first 1. So I see negative 1 plus 3 to the 5th. So we can find that s equals 3 to the 5th minus 1 divided by 3 minus 1, which works out to be 243 minus 1 divided by 2, which happily is 121, as expected. So we find something interesting here. Now, what do we find? What we find here is that for this particular sum, the answer is 3 raised to a power where the power is 1 higher than the exponent appearing in the sum of terms. Then we subtract off 1 and divide by 3 minus 1, the ratio minus 1. And in fact, this is the pattern that we've been searching for. And we can check to see if this pattern holds for other sums. For example, let's apply the analogous pattern with 1 plus 3 squared plus 3 cubed. Well, we would conjecture that the sum would equal 3 to the, not the cube, but we actually increase the power by 1, 3 to the 4th. Then we subtract 1 and divide by 3 minus 1, which equals 81 minus 1 divided by 2, which is 40, which is exactly what we saw earlier. Well, we can now derive a formula for the more general sum. 1 plus 3 squared plus 3 cubed plus all the way out to 3 to the n power, where n is some unknown natural number. Now, we'll again call this sum s for convenience, and we'll just follow the exact same trick as before. One great thing about mathematicians is that once we have a great idea, we try to recycle it again and again. So if we multiply this entire equation by 3, we can align most of those interior terms of s with most of the terms of 3s, and then we could subtract. So we'd have 3s equals 3 plus 3 squared plus 3 cubed plus so on out to 3 to the n plus that last term, which is now 3 to the n plus 1, because we're multiplying that last original term by an extra factor of 3. That's the plus 1 in the exponent. Now underneath this, we just write down the s again. So s equals 1 plus 3 squared and so forth out to 3 to the n. And notice how everything aligns in the interior terms. When we subtract, I see 3s minus s, which is 3 minus 1s. And on the right-hand side, all the interior terms add to give 0, except for that very, very, very far right term, which is 3 to the n plus 1, and that very first term in the bottom sum, which I'm subtracting, so I see a negative 1. And so I see that 3 minus 1 times s equals negative 1 plus 3 to the power n plus 1. Again, solving for s, we see that s equals 3 to the n plus 1 minus 1, all divided by 3 minus 1. Well, we can now consider the corresponding sum for any ratio r. So let's consider 1 plus r squared, and so forth, all the way down to r to the n. Again, we'll call this sum s. If we multiply s by r, that's now the ratio, it used to be 3, we can align most of the terms in s with most of the terms in r times s, just as before, and then subtract. Look at the economy of ideas. We're just taking this one idea and looking at variations on the theme, the variations being the generalization. So we have r times s equals r plus r squared plus r cubed all the way out to plus r to the n plus the last term, r to the n plus 1. Underneath it, aligned, we'll just write s without the extra multiple of r. So we see s equals 1 plus r squared plus r cubed all the way out to plus r to the n. When we subtract, what do we have? On the left-hand side, we have r s's, and we're taking away one s, so that's r minus 1 s's. And on the right, again, we see this enormous cancellation on the interior terms, and we're left with negative 1 plus r to the n plus 1. Solving again for s, we see s equals r to the n plus 1 minus 1 divided by r minus 1. So we see the general manifestation of the formulas we saw with the r equaling 3. Now, Euclid, in fact, derived this formula around 300 BCE. So this formula goes back to antiquity. Now, I want to take a moment to share with you the legend of the most modest mathematician. And here we'll see another example of the sum of a geometric progression. So this is a very old tale, which I really enjoy. So quite a while ago, a king wished to reward a loyal mathematician and asked him what he desired. Well, the mathematician, who by the way appeared both modest and humble, replied that if just 1 grain of rice was placed on a square of an ordinary 8x8 chessboard, and then 2 grains of rice in the next square, and so forth, doubling the previous amount of rice, until the last square on the chessboard was reached, then he would be totally content with the total sum of all the grains of rice. Well, the king laughed and immediately granted this seemingly small request. However, the king quickly stopped laughing, for the number of grains of rice owed to the mathematician equaled the sum of the terms from a geometric progression. Now, let's take a look at this in action for a second. So here we have a chessboard, and so the mathematician asked for 1 grain of rice in the first spot, and now we're considering the geometric progression where we double each time. So the next one would be 2 grains of rice. So there's the 2 grains of rice. If we double again, we'd see 4 grains of rice. And so here I have 4 grains of rice. And the next one would, next square would consist of 8 grains of rice. And you can see that we have these grains of rice. And the next one would be 16 and so forth. And we see the pattern. Okay, now the mathematician wants the sum of all the grains of rice. So we're actually adding up a geometric progression. We're actually adding up 1 plus 2 squared plus 2 cubed plus 2 to the 4th. Now let's just think about it. What's the very last square? 2 to what power? Well, we start with 1, and then we have 2 to the first power. Then we have 2 squared in the third spot. We have 2 to the cubed in the fourth spot, and so on. So what do we see? We see in the last spot, in the 64th spot, we're going to have 2 to the 63rd power. Because notice that we started with a 1 and then went to 2 to the first, 2 to the second in the third spot, 2 to the third power in the fourth spot, and so forth. So in the 64th spot, we'll be at the power 63. So we're adding 1 plus 2 plus 2 squared plus 2 cubed, all the way out to plus 2 to the 63rd power. Well, this is the geometric progression where we have r equals 2, and we're going to sum all the terms up to n equals 63. So our formula tells us the answer. It's 2 raised to the 64th power, that's 63 plus 1. Then we subtract 1 and divide by 2 minus 1, which works out to be a 20-digit number. That's a lot of grains of rice. Now, how can we make sense of this extremely large amount of grains of rice? Well, given that a grain of rice weighs approximately 0.033 grams, this pile of rice would weigh more than 671 billion tons. To place this tonnage in perspective, today the world produces approximately 500 million tons of rice each year. So this would take an awful long time just to grow, well over 1,200 years. Well, needless to say, the king was faced with 2 choices. Either give up his entire kingdom to the mathematician to begin to pay off this enormous debt, or simply have the mathematician executed. Guess who had the last laugh? Anyway, an important moral, both about geometric progressions and how quickly they accumulate when you add them up, and also mathematicians shouldn't be so greedy, especially if they come across as being quite modest. Well, finally, I want us to consider summing up infinitely many numbers from a geometric progression. So first we must ask, when does an infinite sum of terms from a geometric progression even make sense? Well, let's begin by recalling that for any r that's not equal to 1, the formula for the sum of 1 plus r squared plus r cubed all the way out to r to the n, we derive to be r to the n plus 1 minus 1 all divided by r minus 1. That was the formula for the sum of the terms in a geometric progression that we found. Well, we now suppose that the ratio r is a small number. Let's say a positive number that's less than 1. Thus, let's think about it. As n gets larger and larger, r to the n is going to be getting smaller and smaller and is in fact approaching 0. For example, if we let r equal 1/2, then let's look at the geometric progression. We'd have 1/2, a quarter, an eighth, a 16th, a 32nd, a 64th, and you could see that as the denominator gets larger and larger, the actual term, the actual fraction, is getting smaller and smaller and smaller and is heading to 0. Well, in this case, we can actually consider the infinite sum of all the numbers in this geometric progression. Now, this infinite sum is known as a geometric series and is extremely important in our study of number theory. So we will come back to this again and again. Now, a geometric series is an infinite sum of the form 1 plus r squared plus r cubed and so forth, but endlessly. Okay, well, does such an endless sum have a numerical value? As always, we search for a pattern through an example. So let's consider the geometric series 1 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th plus 1/2 to the 5th, and so on, going on forever. Now, if we view these individual terms as representing lengths of a line segment, each one representing a shorter and shorter line segment, then we can see geometrically that this infinite series equals 2. And I want to show that to you right now. So here is a little piece of a number line. And you can see, think of this part here as being 0, this here is 1, and this point here is 2. Now, if we look at the very first term in our sum, we actually see it's 1. So if we consider that length, a line segment of length 1, let me align this up here so we can look at this. This silver pointer is going to represent our sum so far. We're at 1. So there's 1, brings us to 1. Now we add the next term in our series, which is a half. So now I have to go halfway to where I currently am, towards 0. Now I add a quarter, which is halfway from where I currently am. Now I add an eighth, which is halfway. And now I add a 16th. And now I add a 32nd and a 64th. I keep taking half and half and half. And if I do that forever, I will in fact fill up the entire line segment. And so I see that that infinite series actually geometrically seems to fill up this line, so has length length 2, and so therefore the series has a numerical value of 2. Now, let's consider 1 plus a half squared plus a half cubed, and so forth, just up to a half to the nth power. Well, we have the formula for that, finite sum. It's 1 half to the n plus first power minus 1 divided by 1 half minus 1. And now recall that 1 half to the n plus 1 is approaching 0 as the n gets larger and larger and larger. So thus, this formula is heading toward negative 1 divided by 1 half minus 1, which is negative 1 divided by negative a half. The negative signs cancel each other out, and the reciprocal of a half is actually 2, which actually agrees with our geometric analysis from a moment ago. Well, more generally, for any ratio r that's positive but less than 1, we recall that 1 plus r squared plus r cubed and so forth out to plus r to the n equals our formula, now familiar, r to the n plus 1 minus 1 over r minus 1. And the r to the n plus 1 is approaching 0 as n gets larger and larger. Because remember, we're assuming that the r is a positive number that's less than 1. So higher powers will make the thing actually shrink. Thus, we see that the infinite series, 1 plus r squared plus r cubed and so forth, endlessly will actually equal 1 over 1 minus r, just as we saw with the example of the 1 halves. Well, we can apply this formula to find the value, say, of 1 plus a fifth squared plus a fifth cubed and so forth. Here we see that the ratio r equals 1/5, and so what does our formula tell us that this geometric series sums to? It would sum to 1 divided by 1 minus r, which is 1 minus a fifth. Well, 1 minus a fifth is 4/5, so our sum is 1 over 4/5, or the reciprocal of 4/5, which is 5/4. So that infinite series sums to a number, and that number is 5/4. Well, this formula for infinite geometric series is an important identity that we'll utilize as we move deeper and deeper into the world of number theory. So this identity for the sum of an infinite geometric progression, these geometric series, will come back again and again. Well, I want to close this lecture with a prize-winning application. Suppose that you win a $1 million prize on a television game show. Congratulations, by the way. You first believe that you have $1 million to enjoy, which sounds great. However, Uncle Sam has other plans for you. He will take 1/3 of your bounty in tax. However, suppose now that the television network wants to generate so much hype that it offers to actually pay the tax for you. So you'll take home the full $1 million. So they say, oh, they'll give you 1 plus 1/3 million dollars so that you could pay off the 1/3 to the government. However, you still don't take home $1 million. Do you see why? Well, because you now have to pay 1/3 tax on the extra 1/3 million dollars they gave you. That's an extra 1/9 of $1 million in tax that you have to pay additionally. Well, if they offered to pay that extra 1/9 of $1 million, sounds good, but then that's an additional amount which will be taxed as well. So how much must they offer you so that you actually genuinely take home $1 million after taxes? Well, the answer is the infinite geometric series 1 plus a third. Now they got to pay for the tax on a third, which is plus 1/3 squared. Now they have to pay a tax on the 1/3 squared, which is plus 1/3 cubed, plus 1/3 to the fourth, plus 1/3 to the fifth, and so on, forever, endlessly. And what does our formula tell us? Well, here we see the common ratio r is 1/3, so our series sums to 1 over 1 minus r, which in this case is a third, so we see 1 over 1 minus a third. Well, that's 1 over 2/3, and the reciprocal of 2/3 is 3/2. So 3/2 million dollars is what the television program has to provide. And actually, we can see that the tax on this amount is, well, we have a 3/2 million dollars. We multiply that by a third. That gives us $500,000 in taxes we'd have to pay. So if we deduct this amount from the 3/2 million that we have, 3/2, by the way, is 1.5 million. We pay $500,000 in tax, and voila, we see we're left with exactly $1 million after taxes. The power of a geometric series is one that will be with us throughout our course. And the fact that there's such an elegant formula that we ourselves can derive for that infinite sum of ever-shrinking terms in a geometric progression is certainly a work of beauty and is certainly worth $1 million.